Right now, as you listen, you're hurtling through a colossal chasm in the fabric of space, a void so immense it stretches 2 billion light-years across. Imagine that scale for a moment. This isn't science fiction. It's a confirmed reality identified by scientists in 2013, yet largely unknown to the general public. We reside within what cosmologists call the KBC Void, a cosmic desert where the density of matter is a staggering 20% thinner than the cosmic average. This profound emptiness isn't merely a curiosity, it's actively warping our perception of reality itself. From our unique vantage point, the universe appears to be expanding faster than our most fundamental equations predict a discrepancy that has sent ripples through the heart of cosmology. Join us as we journey through the groundbreaking discovery that shattered our cosmic worldview, explore the perplexing reasons why 90% of all space is a vacuum of near-nothingness, and reveal the profound implications of existing in the universe's cosmic outskirts. If you're ready to see the cosmos through a new lens, prepare yourselves. We begin. The story of the KBC Void begins not with grand pronouncements, but with the meticulous, often painstaking work of 3 astronomers counting galaxies. In 2013, Ryan Keenan, Amy Barger, and Lennox Cowie undertook an ambitious survey meticulously mapping the positions of 35,000 galaxies stretching across billions of light-years. As their data coalesced, a startling anomaly emerged. The numbers were unequivocally wrong. Everywhere they looked, in every direction near Earth, there were significantly fewer galaxies than expected. Not a slight deviation, but a consistent deficit of 20%. This colossal underdensity wasn't confined to a small pocket. It radiated outwards for 1 billion light-years in every direction, forming a colossal sphere of cosmic emptiness, with our own Milky Way galaxy nestled eerily close to its centre. This was no ordinary gap between galaxy clusters. This was a void on a scale so immense, so statistically improbable, that it should not exist according to the prevailing standard model of cosmology. The researchers, acutely aware of the implications, rigorously triple-check their data, cross-reference multiple galaxy surveys, and scrutinize the sky from different angles. Yet the result remained stubbornly consistent. Our galaxy, alongside everything within its immediate cosmic neighbourhood, resides inside an underdense bubble of space so massive it utterly dwarfs every other known structure. This monumental discovery was almost ironically given a remarkably understated name, the KBC Void, using the initials of its 3 trailblazing discoverers. But there is nothing casual about what it represents. In the standard model of cosmology, the lambda CDM model of the universe is expected to be remarkably uniform when viewed from a sufficiently zoomed-out perspective. Yes, galaxies are known to cluster together, leaving vast dark spaces between them. That much is entirely expected. But a region this enormous, exhibiting such a significant deficit of matter, pushes the very boundaries of what random chance can explain. Think of it like rolling a die 1,000,000 times and having it land on a 6 every single time. It's not impossible, but you'd certainly question the die. Computer simulations charting the universe's evolution from the Big Bang to the present day rarely produce voids of this extreme size and emptiness. And when they do, it demands exceptionally rare initial conditions. The statistical probability less than 1 in 1,000. Some scientists delving deeper into the mathematics of cosmic structure formation calculated that the KBC Void represents an astonishing 10 sigma deviation from the average density, meaning it is so astronomically unlikely that you might not expect to find even one such void in the entire observable universe. Yet here we are, living precisely inside one. The implications began cascading immediately. If our cosmic address is so statistically unusual, does it fundamentally bias every single measurement we make about the universe? When we calibrate our telescopes to distant supernovae to gauge the universe's expansion rate, are we truly observing the grand overarching cosmic expansion, or merely a distorted localized version unique to our peculiar neighbourhood? The void hypothesis offered a compelling if unsettling answer to one of the biggest mysteries currently plaguing modern cosmology, the infamous Hubble tension. For years, scientists have been grappling with two profoundly precise, yet stubbornly conflicting measurements of the universe's expansion rate. One method, peering back into the ancient universe via the cosmic microwave background, yields a rate of roughly 67 kilometers per second per megaparsec. The other, observing nearby supernova as cosmic distance markers, consistently measures a faster rate of around 73 kilometers per second per megaparsec. That's a 9% disagreement, which in the realm of precision cosmology is not a minor quibble, it's a full-blown crisis. Both measurements are incredibly precise with painstakingly small error margins. Both logically should yield the exact same answer. They do not. But if Earth is indeed situated inside a massive underdense region, a profound gravitational dynamic comes into play. The denser cosmic web surrounding the void would exert a significant gravitational pull, tugging outward on the galaxies within it, including our own. This outward pull would impart an additional velocity to their motion, away from us, making the local expansion appear faster than the true cosmic average. Suddenly, the conflicting measurements began to make disconcerting sense. We weren't necessarily measuring the universe incorrectly. We were measuring it from inside a colossal cosmic hole, a bubble of slightly faster local expansion. This realization profoundly altered our perspective. But it also birthed an uncomfortable existential question that cosmologists are still grappling with. If our location is this uniquely unusual, can we truly trust anything we think we know about the cosmos? What comes next reveals just how strange our cosmic neighbourhood truly is. Cosmic voids, despite their name, are not truly empty. This paradox makes them even stranger than a mere vacuum suggests. Within these vast lonely stretches of space between the scattered isolated galaxies lies a sparse mixture composed primarily of dark matter, dark energy, and occasional wispy filaments of primordial hydrogen gas. The density is so exceedingly low that the very force of gravity barely functions. Without sufficient mass to aggregate and bind things together, the process of structure formation essentially grinds to a halt. No new galaxy clusters can coalesce, no rich superclusters can emerge. The void, by its very nature, remains a void, perpetuating its own emptiness. This profound emptiness has consequences that ripple through the fundamental laws of physics itself. Gravity, already the weakest of the four fundamental forces in nature, requiring enormous masses like planets and stars to exhibit noticeable effects, becomes even less relevant in a void where mass is so scarce. Here the dominant force shifts dramatically. It is dark energy, the mysterious repulsive pressure that accelerates the universe's expansion, that wins decisively. In the dense galactic urban centers of the universe, gravity actively fights against dark energy, acting as a brake slowing down the expansion in those regions. But inside the vast desolate expanse of a void, gravity effectively loses that tug of war. As a result, voids expand faster than the rest of the universe. They grow like colossal, accelerating bubbles, pushing their boundaries relentlessly outward, while the dense filaments of galaxies around them act as rigid confining walls. This creates a self-reinforcing cycle. The more a void expands, the emptier it becomes, which in turn allows for even faster expansion. Scientists have confirmed this through careful, painstaking observation, measuring how galaxies near the edges of voids move compared to those in denser regions. The void galaxies are unequivocally rushing away from the centre, faster than cosmic expansion alone would explain. Something is pushing them outward. That something is the collective gravitational pull from all the denser matter residing outside the... Picture a cosmic void as a vast shallow valley not in terrain but in the gravitational potential of space-time itself. This valley is surrounded by towering mountains of denser matter, the cosmic filaments and clusters. Gravity always seeking to pull things downhill towards greater mass pulls from the valley towards the mountains. In the context of space, this means galaxies within the void are subtly yet relentlessly pulled outward from the void's centre towards the surrounding denser regions. The effect is both measurable and significant. Our own Milky Way galaxy, for instance, is currently accelerating away from the local void, a smaller nearby underdensity at a blistering 600,000 miles per hour. Driven by this profound gravitational imbalance, the interior of a void transforms into a truly bizarre laboratory for physics. Light travelling through it experiences less gravitational influence than light traversing regions of normal denser space. This subtly affects our observations. When astronomers study the cosmic microwave background CMB radiation, the faint afterglow of the Big Bang, they notice that light that has passed through voids appears ever so slightly cooler. This is due to the integrated Sachs-Wolf effect. The reduced gravity in voids causes less gravitational redshift on the CMB photons, showing up as cold spots in temperature maps of the early universe. Crucially, these cold spots align perfectly with where we observe large voids today. This alignment isn't a mere coincidence. It's physics at play, a direct observational fingerprint of these colossal empty regions. Understanding what makes voids empty helps explain why they hold such immense importance for cosmology. They are not merely boring blank spaces between interesting galaxy clusters. They are unique laboratories where dark energy reigns supreme, and where the familiar force of gravity takes an astonishing back seat. By studying how matter behaves differently in voids compared to dense regions, scientists can rigorously test fundamental theories about how the universe works. The KBC Void encompassing our very existence might be unsettling, because it forces us to question our assumed cosmic typicality, but it also offers a rare and invaluable opportunity. We are positioned in precisely the right place to study the universe's most extreme low-density environments. The grand architecture of the universe, the structure that contains these voids, is far stranger and more intricate than anyone initially imagined. The cosmos is not a smooth, homogeneous soup of evenly distributed galaxies. Instead, it astonishingly resembles Swiss cheese, or a complex sponge where dense matter forms colossal walls and intricate filaments that encase and surround truly enormous hollow pockets of emptiness. This foam-like interconnected architecture is aptly named the cosmic web, and it represents the largest known structure in nature. Galaxy clusters, the veritable cities of the universe, concentrate at the intersections where multiple filaments converge, creating luminous nodes of intense matter density. These nodes shine brilliantly with millions of galaxies packed relatively close together. Stretching between them run the filaments themselves, long sinuous chains of galaxy groups that can extend for hundreds of millions of light years. These filaments often coalesce into vast sheet-like structures, immense cosmic walls where galaxies gather in higher than average concentrations. And nestled between these filaments and walls lie the voids silently occupying the vast majority of the universe's volume while containing hardly any of its mass. This intricate, large-scale structure was not always obvious. For decades, astronomers photographed the sky painstakingly cataloguing galaxies. But the true three-dimensional arrangement, the depth and interconnectedness remained tantalizingly hidden. Early distance measurements were notoriously poor. Galaxies that appeared to be next to each other on the two-dimensional celestial sphere might in reality be separated by billions of light years, with one vastly farther away than the other. It was only when scientists began systematically measuring galaxy redshifts in the 1970s and 80s that the cosmic web slowly began to reveal its hidden grandeur. Redshift surveys allowed astronomers to calculate how far away each galaxy was by measuring how much the expansion of space had stretched its light towards redder wavelengths. Suddenly, the distribution snapped into breathtaking focus. The universe possessed structure on scales nobody had ever expected. The first major void discovery, a harbinger of the cosmic web, came in 1978 when two independent teams identified large, underdense regions. This initial glimpse was soon followed by more ambitious surveys, each mapping deeper into space and revealing an increasingly intricate and astonishing web of interconnected structures. The Sloan Digital Sky Survey SDSS which commenced in 2000, ultimately created some of the most spectacular three-dimensional maps spanning billions of light years, showcasing the cosmic web in stunning, intricate detail. These maps depict filaments twisting and branching like vast cosmic blood vessels, while voids appear as dark, expansive bubbles, sometimes spanning an astonishing 500 million light-years across. The largest known structures include the Sloan Great Wall, a filament nearly 1.5 billion light-years long, and on the opposite end of the density spectrum, supervoids like the Eridanus Void stretch an astounding 8 billion light-years wide, containing even fewer galaxies than the KBC Void. Together, these features paint a compelling picture of a universe organised on scales far grander and more complex than early cosmological models predicted. Galaxies, it turns out, are not the fundamental building blocks of the universe. The cosmic web itself is the overarching structure, with galaxies merely marking where the matter happens to concentrate within its intricate latticework. Why does the universe organise itself in this profoundly structured yet largely empty way? The answer reaches back to the very beginning of cosmic time. Immediately after the Big Bang, the distribution of matter was not perfectly uniform. Instead, infinitesimal quantum fluctuations inherent to the probabilistic nature of reality occurred during the universe's first fraction of a second, specifically during an epoch known as cosmic inflation. This brief hyper-accelerated expansion stretched these subatomic quantum jitters from microscopic scales to macroscopic cosmic dimensions. These fluctuations created minuscule variations in the density of matter and energy. Some regions were infinitesimally denser than average, while others were slightly less dense. These differences were almost imperceptible, perhaps 1 part in 100,000, but gravity over cosmic timescales acts as a relentless amplifier. Denser regions possessing a tiny gravitational advantage pulled in slightly more matter, making them even denser. Conversely, less dense regions with a weaker gravitational tug gradually lost matter to their surroundings, becoming progressively emptier. Over hundreds of millions of years, this process snowballed with increasing momentum. Small clumps of matter merged into larger clumps, which then coalesced into the first stars and galaxies, eventually aligning into the vast filaments we observe today. Simultaneously, the underdense regions, continuously losing matter, expanded into the colossal voids. The cosmic web is in essence gravity doing its work over billions of years, transforming barely noticeable initial ripples in the quantum foam of the early universe into the most majestic and intricate architecture in existence. Today, voids occupy roughly 90% of the total volume of space, a staggering figure. Filaments and clusters, despite containing most of the universe's mass, make up the remaining 10%. This extreme imbalance defines the very character of our universe. We live not in a cosmos densely packed with galaxies, but in a cosmos overwhelmingly dominated by emptiness, punctuated by occasional brilliant concentrations of matter. The KBC Void is just one such bubble in this cosmic foam, but it happens to be our bubble, and that makes all the difference for what we observe and how we interpret the universe around us. The next chapter reveals exactly where we sit inside this immense hollow. Our galaxy, the Milky Way, does not sit precisely at the centre of the KBC Void, but it is unequivocally close enough to matter significantly. Measurements place our spiral home somewhere between 200 and 400 million light-years from the void's actual gravitational centre. While that might sound like an unimaginably vast distance, and indeed it is compared to anything humans can experience, the KBC Void extends outward for a full billion light-years in every direction from its centre, making our offset relatively small within its immense volume. We sit comfortably, if somewhat uncomfortably, well within the underdense region, enveloped by the void's low-density environment in all directions. This isn't a random happenstance. This specific position has profound consequences for every astronomical observation we make and every cosmological conclusion we draw. If we were, for example, located entirely outside the void, perhaps nestled within one of the dense cosmic filaments, our measurements of the universe's expansion would look entirely different. we would likely calculate a slower expansion rate, and crucially, the perplexing Hubble tension would simply not exist. Our larger cosmic neighbourhood adds another fascinating layer to this story. The Milky Way belongs to the Local Group, a modest collection of about 80 galaxies, including our giant neighbouring spiral Andromeda. The Local Group itself is merely a small component within the Laniakea supercluster, a truly massive structure containing roughly 100,000 galaxies spread across an astounding 520 million light-years. Laniakea is enormous by any normal standard, a sprawling galactic metropolis. Yet consider this for a moment, even this magnificent supercluster, an aggregation of 100,000 galaxies, still resides entirely within the KBC Void. The Void is so unfathomably vast that it can swallow entire superclusters and still have ample room to spare. Laniakea thus forms part of the sparse population of matter scattered through the Void, one of the rare, moderately dense concentrations in an otherwise barren expanse. The Local Group is also significantly influenced by another nearby underdense region known as the Local Void, which, while distinct, is dynamically connected to the larger KBC Void. The Local Void extends approximately 200 million light-years and sits adjacent to our position. Our galaxy is currently rushing away from it at that incredible speed of 600,000 miles per hour, propelled by the gravitational pull from denser regions beyond. This motion is not merely passive cosmic expansion. It is a peculiar velocity, meaning it results from local gravitational effects rather than the uniform stretching of space itself. These peculiar velocities are a critical complication in efforts to measure the true underlying cosmic expansion rate, as they add an extra layer of motion on top of the expansion signal. Astronomers must meticulously account for these local gravitational effects, but inside a super void, those effects are amplified, more complex, and thus inherently harder to cleanly separate from the global expansion. The void's gravitational influence reaches even farther. When scientists measure the bulk motion of galaxies out to distances of 250 million light-years, they uncover coherent bulk flows that significantly exceed predictions from standard cosmology. Entire regions of space are observed to be moving faster than they should be, flowing in coherent patterns demonstrably driven by the void's immense gravitational imbalance. The KBC Void generates a large-scale velocity field that affects everything within its boundaries. Galaxies are not just passively expanding with the universe in an empty region, they are actively responding to the complex gravitational landscape, accelerating outward from the underdensity drawn towards the denser structures beyond the void's colossal edge. This makes our local patch of the universe far more dynamic and unusual than the calm uniform cosmos assumed by simplistic standard models. Our position inside the void also inherently affects what we can visually perceive. Light from distant galaxies must traverse the void on its journey to our telescopes. This light experiences less gravitational interaction than light travelling through denser regions, creating subtle but measurable effects on the light's wavelength and energy. Moreover, the void itself intrinsically influences the perceived distribution of matter we observe. When we gaze outward from our vantage point within the void, we effectively see the shell of denser material surrounding us in all directions. That shell manifests as a discernible concentration of galaxy clusters and filaments, appearing at a specific range of distances. Beyond this perceived shell, the universe returns to a more typical average density. This creates an unavoidable observational bias. We are not sampling a truly random location in the universe. We are sampling from inside one of its most extreme and unusual features. Living in the void therefore means living with a fundamental, systematic uncertainty about how truly typical our measurements really are. Indeed, every measurement you have ever heard about the universe's expansion rate might in fact be subtly wrong. Not because scientists have made mistakes in their calculations or observations, but because we are measuring from inside a cosmic hole that fundamentally distorts the signal. This profound problem reveals itself most starkly when astronomers employ different methods to calculate the Hubble constant, the fundamental number that quantifies how fast space expands. One method looks at the cosmic microwave background CMB, the ancient light from when the universe was a mere 380,000 years old. This light encodes invaluable information about the early universe's density and expansion rate. Scientists then feed this data into sophisticated cosmological models and calculate what the expansion rate should be today. The answer derived from this primordial data consistently comes out to approximately 67 km/s per megaparsec. This means that for every megaparsec of distance, roughly 3.3 million light-years space expands at 67 km/s. The second independent method looks at nearby objects with known intrinsic brightness, specifically type Ia supernovae and Cepheid variable stars. These luminous objects serve as cosmic measuring sticks, because astronomers understand exactly how bright they should be. By comparing their actual intrinsic brightness to their apparent brightness as seen from Earth, scientists can precisely calculate their distance. Combining these distance measurements with redshift measurements, which indicate how fast they are receding, yields the expansion rate directly. This local method consistently produces a significantly higher number, about 73 km/s per megaparsec. The difference, as we noted, is a persistent 9%. Both measurements are incredibly precise, boasting very small error margins. Both, according to our current understanding of cosmology, should yield the same answer. They do not. This discrepancy is the Hubble tension, and it has reached an astonishing 5 sigma statistical significance, meaning there is less than a 1 in a million chance that it is merely random variation. The KBC Void offers a compelling explanation for why these two numbers stubbornly disagree. When we measure the expansion rate using nearby supernovae, we are by definition conducting our measurement within the void. The void's significantly lower density translates to less gravity pulling back on the expansion. Furthermore, the denser matter from the cosmic web outside the void gravitationally attracts galaxies within it, adding an extra outward velocity component to their motion. Consequently, these galaxies appear to recede faster than they would in a truly typical average region of the universe. This effectively inflates the local Hubble constant measurement. We are not measuring the universe's true global expansion rate. We are measuring the expansion rate plus the void's peculiar velocity field. Crucially, the magnitude of this effect is large enough to account for most, if not all, of the observed tension. When scientists meticulously model how a void of the KBC's estimated size and depth would affect local measurements, they find it could boost the apparent expansion rate by precisely the amount needed to match the higher local observations. But here is where it gets philosophically uncomfortable. If the void robustly explains our local measurements, then those very measurements might be systematically biased by our extraordinary location. Some scientists understandably resist this conclusion because it appears to violate the hallowed cosmological principle, the foundational assumption that Earth does not occupy a special or privileged location in the universe. This principle states that the universe should appear roughly the same from any vantage point once you average over sufficiently large scales. Finding ourselves inside a super void that significantly affects our measurements seems to directly contradict this elegant simplifying idea. Implies we are in an intrinsically unusual location, a notion that profoundly unsettles physicists. Historically, science has progressively discentered humanity from special cosmic positions. Copernicus showed Earth wasn't the centre of the solar system. Later observations confirmed our solar system isn't the centre of the galaxy, and our galaxy isn't the centre of anything. The cosmological principle is the ultimate expression of this trend. Now, are we truly to believe we just happen to live inside one of the largest and most extreme voids ever observed? The statistical improbability deeply bothers many researchers, yet the observational evidence continues to mount the void exists, our measurements are discrepant, and the void's effects match the observations. Whether we like the philosophical implications or not, the universe might actually be, in a sense, lying to us about its expansion rate. Or more precisely, our unique location is causing us to misinterpret what we measure. The crisis this creates in cosmology runs far deeper than most people realize. The Hubble tension is not just an inconvenient disagreement between two numbers, it represents a fundamental challenge to our very understanding of cosmic evolution. Cosmology rests upon a robust theoretical framework called lambda cold dark matter, lambda CDM, or simply the Standard Model of Cosmology. This model has been spectacularly successful at explaining a vast array of observations from diverse sources. It elegantly accounts for the precise temperature fluctuations in the cosmic microwave background, the observed abundance of light elements like hydrogen and helium, the formation of galaxies, and the large-scale structure of the universe itself. For decades it has stood as the consensus model because it works so incredibly well in so many different contexts. But the Hubble tension, now at 5 sigma significance, suggests something crucial is either missing or fundamentally wrong in this otherwise triumphant framework. When a model's predictions disagree with observations at this extreme statistical level, scientists are compelled to take that discrepancy very, very seriously. The tension matters profoundly because the universe's expansion rate determines almost everything else about its cosmic history. If the universe has expanded faster throughout its existence, it would have reached its current immense size in less time, consequently making the universe younger. Current calculations based on the cosmic microwave background place the universe's age at a robust 13.8 billion years. But if the higher local measurement of the Hubble constant 73 km/s MPC were universally correct, the universe might be only 12.7 billion years old. This creates immediate and profound problems. We observe ancient stars in globular clusters that, based on stellar evolution models, appear to be as old as 13 billion years. These stars, by definition, would be older than the universe itself, a cosmic impossibility. This forces us into an uncomfortable corner. Either our age measurements for stars are systematically wrong, our fundamental understanding of stellar physics is deeply flawed, or the higher local Hubble constant simply does not apply to the early universe. None of these options are comfortable to cosmologists. The tension also directly affects our understanding of dark energy, the mysterious repulsive force accelerating cosmic expansion. Dark energy makes up an astounding 68% of the universe's total energy content, according to standard models, but its precise properties depend sensitively on the universe's expansion rate. If the expansion rate is higher than we thought, dark energy's behaviour might be subtly or even dramatically different from current model assumptions. Some researchers have proposed that dark energy is not a constant, but rather evolves for cosmic time, which would be a revolutionary discovery. Others suggest that we need to add entirely new physics to the early universe, perhaps an extra burst of accelerated expansion shortly after the Big Bang. Every proposed solution, however, introduces new complications and demands independent evidence beyond merely resolving the Hubble tension. Dozens of alternative explanations have been put forward, each vying for scientific credibility. Some scientists propose that the measurements themselves contain subtle systematic errors that have been overlooked. Perhaps interstellar dust between galaxies dims supernovae more than accounted for, making them appear farther away, and thus inflating the expansion rate. Or perhaps Cepheid variable stars are cosmic distance markers, behave differently in varying galactic environments, thereby biasing their use. These explanations are rigorously tested and are continually being ruled out as measurement techniques improve and observational precision increases. The consensus among experts is that the measurements themselves are remarkably solid. Other researchers more audaciously suggest modifications to general relativity Einstein's monumental theory of gravity. Perhaps gravity operates slightly differently on vast cosmological scales than we currently think, which would fundamentally alter predictions for cosmic expansion. This route, however, leads into controversial territory because general relativity has passed every other test thrown at it for over a century with exquisite precision. The void hypothesis, by contrast, offers a cleaner, less disruptive solution that requires less radical modification to fundamental physics. It simply states that we are in an unusual cosmic location, and our local measurements reflect that rather than reflecting universal properties. This explanation might bother people philosophically challenging our cosmic humility, but it requires fewer new assumptions than inventing new particles or fundamentally changing the laws of gravity. Recent work has significantly strengthened the void hypothesis by demonstrating that it naturally predicts other observable phenomena. For example, the outflow velocity from the void should affect not just the expansion rate, but also the coherent motion of galaxy clusters in our vicinity. Measurements of these large-scale bulk flows consistently match the void's predictions. The hypothesis is making testable predictions that are in fact being confirmed. Nevertheless, the debate rages on. Not all cosmologists readily accept the void explanation as a complete resolution. Some argue that even a void as large and deep as the KBC cannot produce a big enough effect to fully explain the entire tension. Others point out that supervoids of this magnitude should be exceedingly rare, and finding ourselves in one just as we develop the precision to measure the Hubble constant seems a statistically suspicious coincidence. Perhaps we are interpreting the data incorrectly in some subtle way. The controversy remains unresolved, which is why the Hubble tension continues to be widely referred to as a crisis. It is not just a number that is off, it is a profound signal that our understanding of the cosmos might be incomplete, perhaps fundamentally so. Understanding how gravity creates this mess requires a closer look at how forces operate in these vast empty stretches of space. Gravity inside a void does something truly counterintuitive. It effectively pushes outward instead of pulling inward. This isn't because gravity itself miraculously reverses its attractive nature. The force of gravity always attracts mass toward mass. But the geometry of mass distribution profoundly matters. Imagine standing in a shallow cosmic valley surrounded by towering dense mountains of galaxies and dark matter. Gravity pulls you toward those mountains, which means relative to the valley's center it pulls you away. Inside a cosmic void, galaxies experience precisely this effect. The vast majority of mass lies outside the void, concentrated in the surrounding filaments and clusters of the cosmic web. That exterior matter gravitationally attracts the interior material, relentlessly pulling galaxies outward from the void center toward the denser regions beyond. The result is a systematic outflow, a coherent pattern of galaxies, accelerating away from the underdense region. This outflow is not just theoretical, it is robustly measurable and significant. Astronomers can meticulously track galaxy velocities using redshift measurements combined with independent distance estimates. When they map these velocities around known voids, the pattern is unequivocally clear. Galaxies near void centers are moving faster outward than cosmic expansion alone would predict. The effect is strongest near the void center, gradually weakening toward the edges where matter density gradually increases. For the KBC Void specifically, this outflow adds hundreds of kilometers per second to the velocities of galaxies within its expansive volume. Our own galaxy, the Milky Way, actively participates in this grand pattern. It is moving at 600,000 miles per hour, away from the nearby local void, driven by this colossal gravitational imbalance. This motion combines with other local effects such as the gravitational pull from the massive Virgo cluster to create our galaxy's overall peculiar velocity, its motion relative to the general cosmic expansion. This outflow has critical implications for cosmic expansion measurements. When we observe distant galaxies and measure their redshift, we're seeing a combination of two effects: the pure expansion of space itself and the peculiar motion of galaxies due to local gravity. Normally, scientists can statistically separate these components because peculiar velocities tend to average out when observed over sufficiently large volumes. For every galaxy moving toward you due to local gravity, another galaxy is moving away, and the average peculiar motion tends to zero. But inside a void, these peculiar velocities do not average out. They all predominantly point in the same direction outward from the void center. This creates a systematic bias that inflates the apparent expansion rate when measured from within the void. The problem compounds at different distance scales. Close to the void center, the outflow is rapid. Farther from the center, but still within the void, the outflow is slower. Beyond the void's edge, these peculiar velocities might even reverse direction as matter begins to fall back toward the denser filaments. This complex velocity profile varies dramatically with distance. When astronomers measure the Hubble constant using supernovae at different distances, they are sampling this varying velocity field. If most of their supernovae lie within the void, which they do because we typically observe nearby supernovae due to other observational complications, the measurement gets systematically boosted by the outflow. The further out you measure, the less the void affects the result. This phenomenon precisely predicts that the measured Hubble constant should appear to decrease with increasing distance, and recent observations are beginning to confirm exactly that trend. Modelling these intricate effects requires careful and complex calculations. Scientists must estimate the void's precise size, depth and density profile, then calculate the gravitational potential it creates. That potential in turn dictates how fast material flows outward at each radius. The calculations consistently show that a void roughly 1 billion light-years in radius, with a 20% density deficit, can easily produce the observed velocity anomalies. The striking match between these predictions and observations is compelling enough that many researchers find the void explanation highly persuasive. However, the standard cosmological model still struggles to explain how such a vast and deep void formed in the first place. Computer simulations based on the lambda-cold dark matter model rarely produce voids this extreme. When they do, it requires very specific initial conditions that are statistically highly unlikely. This raises a troubling possibility perhaps our standard cosmological model is missing something fundamental. If voids larger and deeper than expected continue to show up in observations, perhaps structure formation works differently than our current theory predicts. Some scientists propose modified gravity theories where gravity is stronger on large scales, which would enhance structure formation and make big voids more common. Others suggest that the universe is simply more inhomogeneous than assumed, which would also make large voids less surprising. Either way, the backwards gravity in voids is telling us something profoundly important about cosmic evolution. Our motion through this gravitational landscape is frankly faster than anyone expected. The Milky Way is not sitting still in space. It is plummeting through the cosmos at a breathtaking 600,000 miles per hour, roughly 850 times the speed of sound. This incredible velocity does not arise from the expansion of space itself, but from local gravitational effects. Specifically, our galaxy is being pulled away from the local void and toward the denser structures beyond it. The local void, while distinct, is dynamically connected to the larger KBC Void, and it exerts a strong, undeniable influence on our peculiar motion. The void itself isn't literally pushing us. Rather, the deficit of matter within the void means there is significantly less gravitational pull towards its centre compared to the stronger gravitational pull exerted on us by the denser regions outside the void. The denser regions effectively win the gravitational tug-of-war, accelerating our galaxy away from the underdensity. This speed is truly difficult to comprehend. 600,000 Darsentust. Hiesos means the Milky Way travels approximately 167 miles every single second. In a single Earth year, our galaxy moves about 5.2 billion miles through space relative to the void. Yet even at this breakneck pace, the void is so unfathomably vast that our motion barely makes a dent. It would still take hundreds of millions of years to cross from one side of the KBC Void to the other. Meanwhile, the void itself continues its accelerated expansion due to dark energy growing faster than we can ever hope to escape it. We are inside the void now, and we will remain inside it for the foreseeable cosmic future. The local sheet adds another component to our complex motion. This flattened structure of galaxies includes the Milky Way, Andromeda, and other nearby galaxies. This sheet forms one of the gravitational walls of the local void. The entire sheet is observed to be rushing away from the void center at about 260 kilometers, or roughly 580 km. Our galaxy participates in this bulk motion along with its neighbors. The sheet's not static. it is actively being evacuated from the void region, flowing outward like water draining from a colossal depression. This motion has been ongoing for billions of years and will continue for billions more. But there's more to our peculiar velocity than just escaping the void. The Milky Way is also inexorably falling toward the Virgo cluster, a rich concentration of over 2,000 galaxies located about 60 million light-years away. The Virgo cluster possesses enough collective mass to gravitationally attract everything in the surrounding region, including our local group. This adds another significant component to our peculiar velocity, roughly 250 kilometers directed squarely toward Virgo. Simultaneously, the Milky Way and Andromeda are engaged in their own cosmic dance, falling toward each other and destined to collide in about 4 billion years, adding yet another velocity component. When all these complex gravitational influences are meticulously added up, the Milky Way's total peculiar velocity relative to the cosmic microwave background rest frame is about 627 km/s. That is the precise velocity astronomers measure when they observe the dipole pattern in the CMB temperature and asymmetry caused by our motion through the ancient light. These intricate motions matter immensely because they profoundly complicate cosmological measurements. When we observe distant galaxies and measure their redshift, we need to carefully correct for our own motion through space. Otherwise, galaxies in the direction we are moving would appear blue-shifted, and galaxies in the opposite direction would appear more red-shifted, creating a false pattern that mimics cosmic structure. Astronomers have been aware of these necessary corrections for decades and routinely apply them. However, inside a supervoid, these corrections become far more complicated, because the void itself creates large-scale bulk flows that extend over hundreds of millions of light-years. Disentangling the void effect from the true cosmic expansion signal requires extraordinarily careful modelling of the local velocity field. Our remarkably high speed through space is in itself compelling evidence for the void. If we lived in a typical region of average density, our peculiar velocity would be much smaller, perhaps 100 or 200 kilometers at most. The fact that we are moving so fast indicates strong gravitational gradients in our vicinity, precisely what you would expect from being near a colossal underdense region. This velocity is profoundly consistent with the void hypothesis, and would be exceedingly difficult to explain without it. This makes our peculiar motion a key piece of evidence in the ongoing debate over whether the KBC Void exists, and crucially whether it affects our fundamental cosmological measurements. The universe may be subtly lying to us about its expansion rate, but it cannot hide the undeniable fact that we are racing through it at incredible peculiar speeds. This rapid peculiar motion connects to a deeper, more profound principle, that the void fundamentally threatens to violate the cosmological principle. This principle is one of the bedrock assumptions of modern physics, and the KBC Void looms as a potential shatterer of this foundation. The principle states that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means the universe is the same everywhere. No location is special or different from any other when you average over vast regions. Isotropic means the universe looks the same no matter which direction you look. These assumptions simplify the mathematics of cosmology enormously, allowing scientists to model the entire universe using relatively straightforward equations. Without the cosmological principle, the equations become vastly more complicated, and robust predictions become much harder, if not impossible, to make. The principle has been remarkably successful, accurately describing many cosmological observations. But the KBC Void, with its 2 billion light-year span and 20% density deficit, represents a major violation of homogeneity. Even on cosmic scales, the void is not small compared to the observable universe. It represents a significant fraction of the volume within several billion light-years of Earth. More troubling still, we happen to live suspiciously close to the centre of this abnormal structure, a fact that seems to directly contradict the idea that our location is utterly unremarkable. Throughout history, science has progressively removed Earth from any notion of a special position. Copernicus showed Earth was not the centre of the solar system. Later observations revealed the solar system was not the centre of the galaxy, and the galaxy was not the centre of anything. The cosmological principle is the ultimate expression of this trend. Not only is Earth not at the centre, but there is no centre because every location is statistically equivalent. The KBC Void directly challenges that elegant worldview. If we truly live inside an abnormally large underdense region, our location is by definition unusual. Voids are common in the universe, but most are significantly smaller than the KBC Void. Supervoids this large are exceedingly rare. Finding ourselves in one raises profound questions about whether the cosmological principle truly holds, or whether it is only approximately true on scales much, much larger than previously thought. Some scientists calculate that in a universe governed by standard cosmology, a void as large and deep as the KBC Void should be exceedingly rare, perhaps representing a 10 sigma statistical deviation. In a typical random realization of the universe's structure, you might not find one anywhere in the entire observable cosmos, yet we are in one. This suggests either we are incredibly statistically lucky, or the standard model is fundamentally wrong about how large-scale structure forms. Defenders of the cosmological principle argue that the void does not actually violate the principle, because homogeneity only applies at scales of several hundred megaparsecs or larger. The KBC Void is about 600 megaparsecs across, which is right at the very edge of where homogeneity is supposed to kick in. Perhaps the universe is simply less smooth at those scales than we previously assumed. Alternatively, perhaps the void is not as extreme as initial measurements suggest. Different observational techniques sometimes yield slightly different density contrasts for the void. If the true deficit is closer to 10 or 15% rather than 20%, the statistical rarity becomes less severe, though it remains a challenge for standard models. These counterarguments attempt to preserve the cosmological principle, but require accepting that our measurements are less precise than we previously thought. Another defense, though often considered weak, invokes the anthropic principle. Perhaps observers can only exist in certain types of environments. If intelligent life requires galaxies to form, and galaxies form preferentially in moderately dense regions, rather than in the densest clusters or the emptiest voids, then finding ourselves in a slight void might not be surprising. But this argument only truly works if the KBC Void is not as extreme as it appears. A 20% deficit is more than merely mild, and pushes the boundary of what the anthropic principle can comfortably explain away. The debate over the cosmological principle is far from settled. Some researchers believe the void is real and significant, necessitating either profound modifications to cosmology or a philosophical acceptance that Earth occupies a genuinely unusual position. Others believe the void is an observational artifact, or not as extreme as initially reported. Still others propose that the principle holds on even larger scales, and that the apparent violation is merely temporary. Future observations, particularly deeper and wider surveys, should help resolve this profound conundrum. Surveys that map the universe to greater distances and depths will reveal whether large voids are as rare as standard models predict, or whether they are more common than expected. If big voids turn out to be frequent, the cosmological principle might survive, but the standard model would require significant revision. If they remain exceedingly rare, we are left with the uncomfortable task of explaining why we happen to live in one. The very origin of these colossal voids reaches back to the universe's first, most enigmatic moments. The voids we observe today began as infinitesimal, almost immeasurable quantum ripples in the primordial plasma, just a tiny fraction of a second after the Big Bang. During a fleeting but profoundly impactful period known as cosmic inflation, the universe expanded exponentially for an inconceivably short duration, perhaps for a mere 10⁻35 seconds. In this hyper-accelerated expansion, those quantum fluctuations, inherent probabilistic jitters at the subatomic scale, were stretched and frozen into existence, transforming from microscopic irregularities to macroscopic cosmic scale variations. These fluctuations created minuscule differences in the density of matter and energy. In some regions, density was a tiny bit higher than average. In others, it was a tiny bit lower. The variations were incredibly small, about 1 part in 100,000, but they were sufficient to set the grand stage for everything that followed. After inflation abruptly ended, the universe continued expanding, albeit at a much slower, more gradual rate. Matter responding to the relentless pull of gravity began to clump together. This gravitational attraction, however, only amplified the initial density differences. Regions that started ever so slightly denser attracted more matter from their surroundings, making them denser, still creating a powerful positive feedback loop. The denser a region became, the more strongly it pulled matter toward itself. Over millions of years, these overdense regions collapsed and coalesced into the first stars, then the first galaxies, which eventually gathered into clusters of galaxies. Meanwhile, regions that started slightly less dense gradually lost matter to their greedier, denser neighbours. As matter slowly drained away toward the collapsing overdense regions, the underdense regions became even emptier. These underdense regions evolved over billions of years into the vast hollow cosmic voids. This process, known as gravitational instability, thus turned barely perceptible initial ripples into the dramatic large-scale structure we observe today, a testament to gravity's patient, persistent work. The cosmic microwave background, CMB radiation, provides an invaluable snapshot of these density variations when the universe was only 380,000 years old. At that ancient epoch, the variations were still minuscule, visible only as slight temperature differences of about 100 millionths of a degree. But those subtle temperature differences directly correspond to the density differences. Warmer spots had slightly higher density, while cooler spots had slightly lower density. Dedicated satellites like the Cosmic Background Explorer COBE, the Wilkinson Microwave Anisotropy Probe WMAP and the Planck spacecraft have meticulously mapped these temperature variations across the entire sky, with exquisite precision revealing the precise seeds of structure formation. The resulting maps display a mottled pattern of hot and cold spots at various angular scales. This pattern intrinsically encodes the blueprint of future structure. Scientists can take this primordial pattern and run it forward in sophisticated computer simulations to predict how structure should look billions of years later. Those simulations reliably produce a cosmic web of filaments, clusters and voids that closely resembles what we observe today. The remarkable match between these predictions and observations is one of the crowning successes of modern cosmology. However, here is where the tension arises. While simulations reliably produce a cosmic web, they rarely produce voids as large or as deep as the KBC Void. The initial quantum fluctuations were inherently random, so every region had some probability of ending up as a void or a filament. But probability distributions matter. Small voids should be common, medium voids less common, and extremely large voids like the KBC should be exceedingly rare. The KBC Void appears to fall into this extremely rare category, which raises questions about whether our simulations are missing something fundamental. One possibility is that the initial quantum fluctuations were not completely random, but had subtle pre-existing patterns that somehow enhance the formation of large voids. This could happen if inflation did not smooth out structure as uniformly as standard models assume. Another possibility is that gravity works slightly differently on large scales than general relativity predicts, which would fundamentally alter how voids form and evolve. A third option is that the universe simply possesses more variance in its large-scale structure than cosmologists previously expected, making large voids less statistically surprising. Each of these explanations requires further robust evidence. Observations of more distant voids in other parts of the universe would help determine how truly rare the KBC Void is. If similar voids turn up frequently, it suggests the standard model underestimates structure variance. If they remain exceedingly rare, it strengthens the case for modified physics or unusual initial conditions. The quantum origin of voids is both elegant and profoundly unsettling. It means that the cosmic desert we inhabit traces its lineage back to subatomic processes that occurred before atoms even existed. Randomness at the smallest scales propagated upward to create structure at the larger scales. The universe's organization is not designed or predetermined. It is the consequence of random quantum fluctuations relentlessly amplified by gravity over billions of years. This realization is one of the profound, humbling insights of modern cosmology. But it also means that our location within this grand accidental structure is ultimately the result of pure chance. There is no fundamental reason we had to end up in a void rather than in a dense filament. We're here simply because the initial conditions in our particular region happened to be slightly underdense. That cosmic accident of quantum chance 14 billion years ago fundamentally determines what we observe when we look out at the cosmos today. The scale of these empty regions utterly dwarfs human imagination. When you typically picture the universe, you probably envision a sky densely packed with shimmering stars and countless galaxies. But the astonishing reality is almost precisely the opposite. The universe is overwhelmingly, breathtakingly empty. Voids occupy roughly 90% of the total volume of space, a staggering proportion. Galaxies and galaxy clusters, the luminous cities of the cosmos, are crammed into the remaining 10%, packed into intricate filaments and vast walls that meticulously surround these colossal voids. This isn't just empty space in the mundane sense of a vacuum between stars. It's empty in the profound sense that entire regions, hundreds of millions of light years across, contain almost no galaxies at all. If you could somehow travel through a void, you would fly for tens of millions of years at the speed of light without encountering a single galaxy. The isolation would be nearly absolute as silence, broken only by the occasional lonely whisper of a proton. This distribution creates a dramatically lopsided universe. Most of the matter concentrates in a tiny fraction of the total volume. The filaments are crowded with galaxies that constantly interact, merge and evolve rapidly. Star formation as vigorous black holes gorge themselves, and galaxy collisions trigger spectacular bursts of new star creation. Meanwhile, the voids are quiet, almost eerily still. A few lonely dwarf galaxies drift through the profound darkness, separated by immense, incomprehensible distances. These void galaxies evolve at a glacial pace because they rarely interact with neighbours. They tend to be smaller, fainter, and less evolved than their counterparts in dense regions. Star formation within them is sluggish, a slow burn. Many void galaxies contain unexpectedly large amounts of neutral hydrogen gas that has not yet condensed into stars. They are galactic backwaters isolated from the busy, violent highways of the cosmic web. The extreme emptiness of voids naturally raises questions about how truly empty space can be. Even in the heart of voids, dark matter is undeniably present. Dark matter, which makes up about 85% of all matter in the universe, does not interact with light, rendering it invisible to our telescopes. It is detectable only through its subtle but undeniable gravitational effect. In voids, dark matter is far less concentrated than in filaments, but it still exists typically at about 15% of the cosmic average density. That might sound like a lot, but spread over such truly colossal volumes, the amount of dark matter per cubic light year is incredibly, vanishingly tiny. Additionally, voids contain dark energy, the mysterious component driving cosmic acceleration. Dark energy appears to be uniformly distributed throughout space, meaning voids have just as much dark energy per volume as dense regions. In fact, precisely because dark energy does not clump like matter, it becomes the overwhelmingly dominant component in voids where matter is scarce. The intricate interplay between dark matter and dark energy determines void evolution. In the early universe, matter dominated even in underdense regions, and gravity still held sway. As the universe expanded and dark energy became increasingly important, voids began to accelerate their expansion. This acceleration causes voids to grow faster over time, gradually eating into the surrounding filaments. Eventually, if dark energy continues to dominate unabated voids, will consume more and more of the universe. Filaments will thin out, and galaxy clusters will become isolated islands in an ever-expanding ocean of emptiness. Billions of years in the future, the universe will be even emptier than it is now, with voids occupying an even larger fraction of the total volume. This stark future evolution is an inevitable consequence given what we currently understand about dark energy. The universe's destiny is to become increasingly hollow. Understanding the void fraction of the universe is critical for accurately interpreting our cosmological observations. When we measure the average properties of the universe, such as the overall matter density, or the expansion rate, we are inherently averaging over both voids and filaments. If we do not account for the profound fact that most of space is void, we risk misinterpreting what those averages truly mean. For instance, measurements of the cosmic microwave background yield the average matter density of the universe, which is about 30% of the critical density needed to halt cosmic expansion. But that average includes both the dense filaments and the sparse voids. The local density varies dramatically depending on where you are. In a filament, the density might be 3 times the average. In a void, it might be only 15% of the average. These colossal variations critically matter when trying to understand local observations. The 90% void fraction also significantly affects searches for rare astronomical phenomena. For example, astronomers searching for distant supernovae or gamma-ray bursts are statistically most likely to find them in the dense filaments where star formation is active and vigorous. Finding these energetic events in voids is much rarer, because voids simply contain fewer galaxies and far less active star formation. This creates a significant observational selection effect. Most of the interesting astronomical events happen in the busy active 10% of the universe, not the quiet, desolate 90%. Consequently, we tend to study the universe from within these active regions, and largely ignore the empty ones. But the voids are just as much a fundamental part of cosmic reality as the filaments. Understanding them is absolutely essential for understanding the universe as a coherent whole. One particular void stands out as particularly impossible under current physics. The KBC Void, by its very existence, defies probability in a way that makes cosmologists deeply uncomfortable. Standard cosmology predicts that structures form through the relentless gravitational collapse of initial density fluctuations. The larger and deeper a structure is, the rarer it should inherently be. Small voids spanning a few tens of millions of light years across are common because they arise from common small fluctuations. Large voids, hundreds of millions of light years across, are less common because they require larger, rarer fluctuations. But the KBC Void is an astounding 2 billion light years across and is 20% underdense. Computer simulations of structure formation utilizing the lambda cold dark matter model rarely produce anything this extreme. When researchers run thousands of simulated universes and meticulously search for voids as large and deep as the KBC Void, they find very few, if any, matches. The statistical likelihood of such a void existing in our observable universe is exceedingly low. Some studies have even estimated the utter improbability. One analysis calculated that a void of the KBC's size and depth represents an astonishing 10 sigma deviation from the expected density. In statistics, a 5 sigma result means there is less than a 1 in a million chance of it being random. A 10 sigma result is almost incomprehensibly unlikely. You would theoretically need to observe trillions of universe-size volumes to expect to find even one such void. Yet here we are, living precisely in one. This is not a small statistical anomaly. It is a massive crimson red flag suggesting something is fundamentally wrong with either the observations or the prevailing cosmological model. If the observations are indeed correct, and multiple independent studies consistently suggest they are, then the model must be missing something crucial. One possibility is that the initial density fluctuations after the Big Bang were not as smooth and perfectly random as standard inflation models predict. If inflation produced more power on large scales than expected, large voids would form more easily and frequently. This would necessitate fundamentally modifying our understanding of inflation, which is already a highly speculative part of cosmology, with limited direct observational evidence. Another possibility is that structure formation proceeded faster or differently than standard models predict. If gravity was effectively stronger in the past, or if dark matter behaves differently than currently assumed structure would form more vigorously, potentially creating larger voids and richer clusters. Some researchers propose modified gravity theories where the strength of gravity varies with scale or environment. These theories can enhance structure formation and make large voids more likely. A third option is that the KBC Void is simply not as extreme as initial measurements suggest. Perhaps observational biases or subtle systematic errors in galaxy surveys have made the void appear deeper and larger than it truly is. Different research groups using different datasets have indeed measured the void's properties and found somewhat different results. Some studies find a 20% density deficit, while others find closer to 10 or 15%. If the true deficit is on the lower end, the statistical rarity becomes less severe, though it still remains a significant challenge for standard models. Confirming the void's exact properties requires substantially more data, particularly deeper galaxy surveys, that can map the void's full extent and density profile with much higher precision. Future missions like the Euclid Space Telescope and the Vera-Rubin Observatory are poised to provide vastly superior data in the coming years. The very existence of the KBC Void has perhaps inevitably become powerful ammunition in ongoing debates about the standard cosmological model. Critics of lambda-cold dark matter point to the void as compelling evidence that the model fails on large scales. They argue that structure formation is not as well understood as we believe, and that the standard model makes incorrect predictions. Defenders of the model conversely argue that rare events sometimes happen, and that finding ourselves in a statistical outlier is not impossible, merely unlikely. They also correctly note that other aspects of cosmology, such as the cosmic microwave background, match lambda-cold dark matter predictions with exquisite accuracy. Abandoning or significantly modifying such a successful model based on one anomalous structure seems premature, they contend. Nevertheless, the void cannot simply be dismissed. It is a real observed phenomenon that demands a robust explanation. Either we accept that we happen to live in an exceptionally rare location, which violates the spirit of the cosmological principle, or we must modify our models to make large voids more common, which requires changing fundamental assumptions about inflation, dark matter, or gravity. Neither option is entirely satisfying. Both represent major paradigm-shifting changes in how we think about the fundamental nature of the universe. The KBC Void has thus become a critical focal point for cosmological debates precisely because it sits at the intersection of observation and theory, challenging our most basic assumptions about how the universe works. Until this profound tension is resolved, the void remains a cosmic puzzle that steadfastly refuses to fit neatly into our current understanding. These vast regions of emptiness serve an unexpected and incredibly important scientific purpose. Cosmic voids are paradoxically the best places in the entire universe to study dark energy, primarily because they are the only regions where dark energy dominates completely and almost unimpeded. In dense areas like galaxy clusters, gravity is powerful enough to successfully resist cosmic expansion. Clusters actively hold themselves together gravitationally, despite the universe expanding around them. Even on slightly larger scales in the cosmic filaments, gravity remains relevant, subtly slowing the expansion of space in those regions. But in voids, where matter is so incredibly sparse, gravity becomes negligible, a whisper lost in the immense silence. With no significant gravitational pull to counteract it, dark energy controls what happens. The voids expand faster than the cosmic average, relentlessly driven by dark energy's repulsive pressure. This makes voids natural uncontaminated laboratories for directly measuring dark energy's strength and properties. Dark energy is without question one of the most mysterious and enigmatic components of the universe. Discovered serendipitously in 1998 through observations of distant supernovae dark energy accounts for an astonishing 68% of the universe's total energy content. It behaves in direct opposition to normal matter and gravity. Where gravity pulls things together, dark energy pushes space apart, accelerating cosmic expansion. The exact nature of dark energy remains a profound unknown. It could be a simple cosmological constant, an unchanging energy density built into the very fabric of space-time itself, or it could be a dynamic evolving field that varies in strength over both time and space. Distinguishing between these possibilities requires incredibly precise measurements of how expansion accelerates in different environments and at different times in cosmic history. Voids critically provide a much cleaner signal for these measurements than dense regions. In dense areas, gravity complicates everything, and the local gravitational pull from nearby masses dramatically affects galaxy motions, making it exceedingly difficult to cleanly separate the signal of cosmic expansion from local gravitational effects. In voids, those complications are minimal. Galaxies move almost entirely due to cosmic expansion and dark energy. By meticulously measuring how fast voids expand compared to predictions, scientists can rigorously test whether dark energy behaves as a constant or whether it subtly changes. If dark energy is observed to be stronger in voids than elsewhere, or if its properties were different in the past that would manifest as detectable deviations from expected void expansion rates. Another powerful way voids assist in our quest to understand dark energy is through their very shape. Dark energy affects not just how fast the universe expands, but also how it expands in different directions. If dark energy is truly uniform throughout space, voids should expand equally in all directions, maintaining a generally spherical shape. But if dark energy possesses subtle variations, or if there are other unknown forces at play, voids might expand more in some directions than others, becoming elongated or distorted. Observations of void shapes can therefore reveal whether dark energy is uniform or possesses hidden structure. Current measurements indicate that most large voids are indeed roughly spherical, which supports the idea that dark energy is uniform. However, the measurements are not yet precise enough to definitively rule out small variations. Improved surveys in the coming years with higher resolution mapping will provide much better shape measurements. The expansion history of voids also deeply encodes information about dark energy. Voids have been growing for billions of years, and their current size reflects that entire long history. By modelling how a void should grow over time given different dark energy properties, scientists can compare these predictions to observations and constrain what dark energy must be like. For example, if dark energy was weaker in the distant past and became stronger, more recently, voids would have grown slowly at first and then dramatically accelerated. If dark energy has been a constant, voids should grow at a steady accelerating pace determined by that constant value. Observations of voids at different distances, which corresponds to observing them at different times in the past, allow scientists to test these competing scenarios. One particularly useful technique involves measuring void edges. The boundary between a void and a surrounding filament is a crucial transition zone where matter density rises sharply. This boundary evolves over time as matter gradually drains out of the void and accumulates in the filaments. The sharpness and precise location of this edge depends sensitively on how fast the void is expanding, which in turn depends directly on dark energy. By meticulously mapping void edges at different cosmic times and comparing them to advanced simulations, researchers can infer how dark energy has influenced void growth throughout cosmic history. Early results suggest dark energy has been roughly constant over the past several billion years, consistent with the simplest models. But ongoing studies are refining these results and diligently searching for any deviations that might hint at more complex dynamic behaviour. Studying dark energy through the lens of cosmic voids is an incredibly active and promising area of research. Future surveys are poised to discover and characterize thousands of voids at various distances and sizes, each void providing an independent, valuable measurement of dark energy's effects. Combining myriad such measurements will dramatically improve our understanding. If voids reveal that dark energy is changing or possesses hidden structure that would revolutionize cosmology, sending shockwaves through our scientific understanding, even confirming that dark energy is indeed constant and uniform would be profoundly important, because it would definitively rule out many alternative theories. Either way, voids are proving to be essential tools for probing one of the universe's deepest and most persistent mysteries. The KBC Void, being the largest and closest supervoid, offers the absolute best opportunity for detailed high-precision study. Its relative proximity allows for measurements that are simply impossible for more distant voids, making it a unique cosmic laboratory. Galaxies that manage to form and persist within these cosmic deserts face unique and profound challenges. Galaxies inside cosmic voids truly grow up in profound loneliness. Unlike galaxies in dense clusters which frequently interact, merge and gravitationally disrupt their neighbours, void galaxies evolve in almost complete isolation. This stark environmental difference shapes everything about their existence and evolution. Void galaxies tend to be smaller and dimmer than galaxies found in the crowded filaments and clusters. They typically possess lower masses containing fewer stars and less overall matter. Many void galaxies are classified as dwarf galaxies, barely massive enough to hold on to their vital gas against the outward pressure from stellar winds and nascent star formation. Their extreme isolation means they rarely, if ever, experience the dramatic galaxy mergers that are so common and influential in dense regions. Mergers are a primary driver of galaxy evolution, triggering spectacular bursts of star formation and feeding the central supermassive black holes. Without these mergers, void galaxies evolve far more slowly and remain in a sense less developed or transformed. Star formation in void galaxies is generally lower than in cluster galaxies, a straightforward consequence of isolation, yet there's a twist. While most void galaxies build stars slowly and steadily, a larger fraction than expected are observed in starburst phases, brief intense episodes of rapid star formation. The paradox dissolves once you consider gas supply. Void galaxies are unusually gas-rich, holding vast reservoirs of neutral hydrogen that linger because external triggers are scarce. In clusters, encounters strip or ignite gas and quickly deplete it. In voids, gas is retained for eons. When star formation finally lights up, likely via internal disk instabilities or stochastic feedback cycles, there's abundant fuel, so the system flares, consumes gas rapidly, then subsides back to quiescence. Morphology diverges accordingly. Void galaxies are predominantly late-type spirals and irregulars, not the merger-built ellipticals common in clusters. With few disruptive encounters, disks remain intact. Spiral arms stay, delicate velocity fields remain regular, and surface brightness profiles look undisturbed, almost paused in cosmic time. These systems are pristine laboratories for isolating secular internal evolution from environmentally driven transformation, providing a baseline against which the accelerated interaction, rich histories of dense regions can be compared. Dark matter halos in voids offer another clue. Every galaxy sits in an extended invisible halo that dominates its mass. In clusters, tidal forces from neighbours stretch and distort halos. In voids, halos remain more spherical and dynamically quiet, making them cleaner testbeds for models of halo structure and feedback. Yet the smallest halos confront a hard floor below a threshold, roughly corresponding to circular velocities. 35 km gravity is too weak to retain and cool gas efficiently. Star formation stalls entirely. This naturally explains why voids are not flooded with countless ultra-faint dwarf sub-threshold halos exist, but they stay dark. Chemistry complicates the picture in productive ways. Slower star formation and fewer mergers suggest void galaxies should be less chemically enriched. Observations confirm lower metallicities on average, but not as dramatically as naive models predict. Some void systems show abundances comparable to counterparts in normal environments. The likely culprits are gas inflows, outflows, and recycling that shuffle metals between disks' halos and the intergalactic medium. Tracking void galaxies across look-back time suggests slow, steady evolution, with fewer catastrophic events making them valuable probes of intrinsic galaxy physics. Next-generation surveys will push to fainter systems and larger samples, testing whether our formation models miss processes that only reveal themselves in the quiet of the void. Scale up and the story becomes stranger. Comes the Laniakea supercluster, identified in 2014, redefines our neighbourhood. Spanning 520 million light-years and containing 100,000 galaxies, Laniakea acts like a matter watershed. Galaxies flow along spacetime's curvature toward a central basin called the Great Attractor. Coherent velocity fields knit the structure together, overcoming local Hubble expansion on these scales. Our Milky Way lies on Laniakea's outskirts, carried by this grand gravitational drainage. Here's the paradox: Laniakea, enormous as it is, resides inside the KBC Void. How can a supercluster inhabit an underdense region? The key is scale. The KBC Void is defined relative to the cosmic mean over billions of light-years. It isn't uniformly empty. It contains filaments, groups and clusters embedded in a volume that is on average matter-poor. Laniakea is large compared with typical superclusters, yet small compared with the void itself. The void's central deficit is the absence of rich superclusters and massive clusters near its core. Density ramps up toward its boundaries hundreds of millions of light-years away. Structure and underdensity coexist, each meaningful on different scales. Meticulous velocity mapping clarifies this hierarchy. Three-dimensional flow reconstructions show galaxies nearer the Great Attractor, accelerating more rapidly, while those at Laniakea's margins are only beginning to feel its pull. These flows delineate Laniakea's boundary. Matter streaming toward the basin is in, and matter streaming elsewhere belongs to neighbouring basins. Our peculiar velocity points toward the Great Attractor, cementing our membership. Yet Laniakea itself is moving, drawn toward the even more massive Shapley supercluster, 650 million light-years away. The result is a nested ladder of motion galaxies into clusters, clusters into superclusters, superclusters toward grander attractors. The KBC Void superposes an outward component on this choreography. Galaxies flow toward local attractors, while also drifting away from the void's centre, producing complex anisotropic velocity fields. This explains why we are not at the void's geometric centre. We occupy an offset, moderately overdense patch that remains underdense relative to the cosmic mean. Laniakea is a respectable concentration of matter, but not enough to erase the broader deficit. The paradox dissolves. Void statistics describe averages across billions of light-years. Laniakea describes dynamics across hundreds of millions. Both are real. Each governs different questions. Pinning down these structures relies on a ruler forged in the infant universe Baryon Acoustic Oscillations (BAO). In the first 380,000 years after the Big Bang sound waves rippled through the hot plasma of photons and baryons, when the universe cooled and recombination locked photons free, the waves froze, leaving a preferred separation scale, about 490 million light-years today, in the distribution of matter. Because the underlying physics is crisp and calculable, this Bow scale functions as a standard ruler across cosmic time. Measure how large the ruler appears at different redshifts, and you map the expansion history with geometric robustness, largely immune to systematics that plague brightness-based methods. Massive redshift surveys Sloan BOSS, and now DESI use BAO to chart the three-dimensional cosmic web with exquisite precision. These maps lay bare the filaments and voids and crucially diagnose our local environment. In our region, BAO-calibrated clustering reveals a statistically significant deficit of matter relative to what you'd predict by extrapolating from distant samples an unmistakable void signature. Galaxies within this underdensity also show slightly higher redshifts than BAO distances alone would suggest, consistent with an outward peculiar velocity superposed on Hubble flow, exactly what a large void predicts. The BAO evidence carries two powerful implications. First, it provides an independent confirmation of the KBC Void's depth and scale, complementing galaxy counts, velocity flows, and other probes. Second, it shows that the Hubble tension, the mismatch between local and early universe expansion rates, appears across multiple methods, not just supernova distance ladders. If local measurements are biased high because we live in an underdensity with outward flows, then stepping beyond the void should yield a lower globally consistent expansion rate, in line with early universe inferences. DC now maps tens of millions of galaxies and quasars with unprecedented fidelity, tightening BAO constraints and enabling finer tomography of the void's geometry and velocity field. Within a few years, uncertainties on the void's depth and radius should shrink to a few percent. If the refined maps show that correcting for our void environment reconciles local and global expansion, rates the standard cosmological model stands, and our tension becomes a lesson in selection effects. If even after those corrections a residual discrepancy persists, the data will point beyond environment to new ingredients in cosmic physics. Either outcome is progress. Voids have moved from being empty afterthoughts to precision laboratories. In their quiet galaxies keep their gas disks and histories intact. On larger scales, coherent flows and BAO reveal how space-time itself steers matter. Together, Laniakea and the KBC Void show that location matters to understand the universe. We must first understand the lens of our own cosmic address. The temperature of the universe itself carries the quiet signature of cosmic voids. The cosmic microwave background CMB, the faint afterglow of the Big Bang, fills all of space at a nearly uniform temperature of 2.7 Kelvin. Yet that uniformity is not perfect. Tiny variations, just millionths of a degree, mark the primordial blueprint of structure. Slightly warmer regions correspond to higher early density, cooler regions to lower density. From these minute ripples, all galaxies and clusters were born. But the CMB also records what happened long after those beginnings. As its photons travelled for 13.8 billion years, they passed through vast structures, including voids, leaving behind subtle imprints. When light enters a void, it experiences less gravitational pull than it would in denser regions. This produces the integrated Sachs-Wolf effect ISW. In a static universe, photons would gain and lose equal energy as they fall into and out of gravitational wells, cancelling perfectly. But because dark energy causes space to expand as they pass through, the energy loss dominates. The result is a tiny measurable cooling of the CMB in the direction of voids. Surveys mapping both galaxies and CMB temperatures confirm this prediction. When astronomers compared the CMB's temperature toward known voids, they found those regions to be about 10 microkelvin cooler than average, precisely what the ISW effect forecasts. The correlation is statistically significant, showing that voids subtly influence the oldest light in the universe. For the KBC Void, which spans nearly 1 billion light-years, the effect should be stronger still. CMB photons cross nearly its full extent, before reaching us, accumulating that small energy loss along the way. One of the most famous features in the CMB is the cold spot, a region about 5 degrees wide and roughly 100 microkelvin cooler than its surroundings. It is unusually large and cold, far exceeding normal statistical fluctuations. One plausible explanation is that a vast supervoid lies along our line of sight, producing the observed chill through the ISW effect. Observations have found a mild underdensity in that direction, but it may not be deep enough to explain the full anomaly. The KBC Void itself is not aligned with the cold spot. Instead, it surrounds us evenly in all directions. Its effect would therefore appear as a global diffuse distortion of the CMB rather than a localized blemish. Detecting such a faint non-localized signal requires precise modelling of what the CMB should look like with and without the void's influence. So far, analyses indicate consistency. The void's predicted effect fits current data, but no decisive detection yet. Future higher precision measurements will determine whether the KBC Void truly leaves a measurable fingerprint on the CMB's temperature pattern. The CMB also constrains how extreme the void can be. If it were significantly deeper or larger, its temperature signature would already stand out clearly. The absence of any dramatic anomaly suggests a moderate density deficit of about 20% over roughly 1 billion light-years, matching independent observations. This coherence between methods strengthens confidence that we inhabit a large but not unprecedented underdense region. Still, the KBC Void has forced scientists to reconsider even gravity itself. Einstein's general relativity, the foundation of modern cosmology, has survived every experimental test for over a century. Yet if a void this vast cannot arise naturally in simulations governed by standard gravity and dark matter, perhaps gravity behaves differently on cosmic scales. Enter modified Newtonian dynamics, MOND, proposed by physicist Mordechai Milgrom in 1983. MOND suggests gravity strengthens slightly when accelerations become extremely small, far below those experienced on Earth or within the solar system. This idea was first used to explain why galaxies rotate faster than visible matter predicts, without invoking invisible dark matter. On cosmic scales, MOND's enhanced long-range gravity causes matter to clump more efficiently, producing deeper voids and richer filaments. Simulations using MOND naturally generate voids the size of the KBC without requiring improbable initial conditions. In such models, the KBC Void is not an unlikely coincidence, but an expected outcome of structure formation. However, MOND has its weaknesses. It struggles to reproduce the finely detailed temperature fluctuations in the CMB that standard cosmology explains beautifully. It also fails to match observed gravitational lensing the bending of light by massive clusters, which clearly requires more gravity than visible matter, plus MOND can supply. Some hybrid models mix MOND with a small amount of dark matter, often in the form of massive neutrinos attempting to retain its advantages while fixing its flaws. Other modified gravity theories change not the strength of gravity, but how it propagates through space. Some propose additional fields or extra dimensions that subtly alter gravitational behavior on large scales, while preserving general relativity locally. These models often predict stronger gravity in low-density regions like voids, naturally easing the formation of such enormous structures. Testing these ideas demands extraordinarily precise measurements of how galaxies move inside and around voids. Detecting systematic deviations from Einstein's predictions, there would be a clear sign of new physics. For now, the debate remains unsettled. Advocates of modified gravity point to the KBC Void, the Shapley supercluster, and the Sloan Great Wall, immense features that seem too extreme for standard LCDM simulations, as evidence that the universe forms structure more vigorously than theory allows. Defenders of the standard model counter that every alternative theory creates fresh problems elsewhere from the CMB to galaxy clustering, and that accepting a statistically rare location is less radical than rewriting gravity itself. Upcoming surveys will likely decide which view survives. If more enormous voids and superstructures are found, modified gravity will gain ground. If not, LCDM endures, but at the cost of admitting that our cosmic address is exceptionally unusual. The KBC Void even threatens our calculation of the universe's age. According to the CMB, the cosmos is 13.8 billion years old. This number depends on parameters: Hubble expansion rate, matter density, and dark energy fraction, that together model how space has stretched since the Big Bang. But if our local expansion rate, around 73 km² per megaparsec, truly reflects the cosmic average, rather than being inflated by the void, then the universe must have expanded faster throughout its history. A faster expansion means a younger universe about 12.7 billion years old instead of 13.8. That seemingly small difference creates a major contradiction. The oldest globular clusters, dense swarms of ancient stars, appear to be about 13 billion years old. Stars cannot be older than the universe that formed them. These stellar ages come from well-understood physics stars of different masses, exhaust hydrogen at different rates, and by observing which ones have left the main sequence, astronomers can date when the cluster formed. Unless stellar evolution theory is systematically off by hundreds of millions of years, the discrepancy cannot be ignored. Some suggest revising those models slightly downward, but doing so precisely enough to fit a younger universe feels contrived. Thus, the tension circles back to the same suspect, the void. If our local region expands faster than average, our inferred Hubble constant, and therefore our apparent cosmic age, will be biased. Beyond the void, the global rate and the CMB's 13.8 billion year age may still hold true. Whether the answer lies in subtle local distortions or a deeper modification of gravity, the message is clear. The universe is not perfectly smooth, and our vantage point matters. The KBC Void has turned a patch of cosmic emptiness into one of the most revealing laboratories for testing the very laws that govern space-time and the birth of everything. White dwarf cooling times provide an independent way to measure the universe's age beyond stellar evolution models. White dwarfs, the dense cores of dead stars, cool steadily over billions of years. The coolest ones observed have been cooling for about 12 to 13 billion years, implying that the universe must be at least that old. These measurements are largely model-independent, making them difficult to tune or dismiss. Like the Hubble tension, the age tension could be elegantly resolved if the local expansion rate does not represent the cosmic average. If the void inflates our local H0, then the 13.8 billion year age derived from the cosmic microwave background could still be correct, leaving enough time for all known stars and white dwarfs to exist, though it would mean accepting that we occupy an unusual location in space. Another possible compromise is that both sides are partly right, if dark energy itself has changed over time. If dark energy was weaker in the past and only strengthened recently, early expansion would have been slower, making the universe older than the high local H0 suggests. This scenario is speculative but not excluded by current data. The age problem reveals a deeper issue. Cosmological parameters are tightly interconnected. Changing H0 affects not only the universe's age, but also the matter density, the nature of dark energy, and the predictions for structure formation. You cannot adjust one variable without shaking the entire framework. The KBC Void offers the simplest way to preserve most of the standard model by attributing the discrepancies to our biased location. Yet it doesn't fully remove the age tension, since part of the evidence for the universe's age comes from local objects such as our own galaxy's globular clusters. These local age estimates should not be affected by the void's impact on expansion, yet they align more closely with the CMB age of 8 billion years than with the 12.7 billion year age implied by the local H0. This internal consistency suggests that the void explanation, while appealing, may not tell the whole story. Ancient starlight from the oldest stars poses another challenge to any model that makes the universe significantly younger. The most metal-poor stars, those with almost no elements heavier than helium, must have formed very early, before much enrichment occurred. Measuring stellar ages requires deep knowledge of stellar structure and evolution. Stars spend most of their lives on the main sequence, burning hydrogen in their cores. Massive stars burn fast and die young. Low-mass stars burn slowly and live for hundreds of billions of years. In clusters, the point where stars begin to leave the main sequence, the turn-off point reveals the cluster's age. Multiple independent methods consistently yield ages around 12.5 to 13 billion years, with uncertainties of only a few hundred million years. The Gaia mission revolutionized these measurements by providing highly precise parallax distances to globular clusters, allowing accurate absolute brightness and removing a key uncertainty. The results confirm that the oldest clusters are about 13 billion years old. If the universe were only 12.7 billion years old, as the high local H0 implies, these stars could not exist. Either stellar ages are wrong unlikely, or the cosmic age from the CMB is wrong also unlikely, or the local H0 is inflated, making the void a reasonable suspect. Yet the situation is more subtle. The oldest stars are local inside our own galaxy. If the void distorts large-scale measurements through light travelling across it, could it also affect stellar ages? One side argues, no, a star's age depends on nuclear physics, not on cosmic expansion. The other side counters that the conditions for star formation depend on when the galaxy itself formed, which in turn depends on local cosmic history. This debate cuts to a fundamental question. How much does our environment affect local versus cosmic observations? Measurements involving distant light clearly depend on the void, but measurements of nearby objects should not. The age tension might therefore mean the high local H0 reflects a genuine global problem, requiring new physics, or more modestly, that stellar models still hide subtle uncertainties. The question remains open. Galaxies add another complication. They do not sit still. They move through space under the gravitational influence of surrounding structures. These motions, called peculiar velocities, are deviations from the smooth cosmic expansion. On very large scales, such motions should average out, producing nearly zero bulk flow if the universe is truly homogeneous. Yet observations reveal coherent flows extending 200–300 million light-years, with speeds of about 400 kilometers, far larger than standard LCDM predicts. A vast underdensity like the KBC Void naturally explains the material inside the void accelerates outward, pulled toward denser filaments at its edges, producing a systematic flow away from the void center. Measuring bulk flow is challenging because redshift combines expansion and peculiar motion. Independent distance estimates such as the Tully-Fisher relation for spirals and the fundamental plane relation for ellipticals allow astronomers to separate the two. The Cosmic Flows project mapped thousands of galaxies and found velocity fields matching models that include the KBC Void. The flows are strongest near the void's boundary, directed outward, and reach magnitudes consistent with a 20% density deficit extending roughly 1 billion light-years. The fit between observation and simulation is striking. Without a void, LCDM struggles to explain these strong flows. Its predictions fall short by a factor of 4. Increasing initial density fluctuations could boost the flows, but that would require statistically improbable conditions and equally uncomfortable explanation. Some cosmologists take the mismatch as evidence that LCDM is incomplete, perhaps missing something in its treatment of dark matter, dark energy, or even gravity itself. Modified gravity theories like MOND predict stronger flows naturally, since they enhance structure formation on large scales. The observed flows fit MOND's predictions without invoking rare fluctuations, though modified gravity faces its own problems. Future surveys will extend measurements farther. If strong flows persist beyond 300 million light-years, it would seriously challenge standard cosmology. If they fade, the KBC Void may simply be a local feature. Remarkably, the KBC Void is not even the most famous underdensity. That title belongs to the Eridanus supervoid linked to the cold spot in the CMB, an anomalously cool region, about 10 degrees wide and 70 microkelvin below average. The cold spot led astronomers to a massive void, roughly 1.8 billion light-years across, revealed by the integrated Sachs-Wolf effect as CMB photons lost energy passing through it. Discovering a structure this large first through temperature anomalies, then confirming it with galaxy surveys, underscores a key truth. Voids are not merely empty spaces on cosmic maps. They leave measurable fingerprints on radiation and motion across the universe. In summary, stellar and white dwarf ages set a lower bound of about 13 billion years. The CMB gives 13.8 billion. The high local H0 lowers it to 12.7, and the strong bulk flows and cold spot both point toward an unusual local environment. The most economical interpretation is that we live inside a vast void where many of our measurements are subtly biased by local conditions. If after probing well beyond this 2 billion light-year bubble the tensions persist, then new physics may indeed be required. Either way, the lesson is clear: the universe is not perfectly smooth. It has structure, bias and perspective, and to know the whole, we must first learn how our small corner distorts the view. The cold spot, discovered by the Wilkinson Microwave Anisotropy probe in 2005, remains one of the most puzzling anomalies in modern cosmology. Its immense size and unusually low temperature make it statistically rare, something that should occur in only about 2% of simulated universes. Early speculation ranged from the mundane to the exotic, a simple statistical fluke, a data processing artifact, or even evidence of a collision between our universe and another in a vast multiverse. Yet the signal persisted across independent observations, including those from the Planck satellite. It was real, but what was it? Astronomers soon discovered that the cold spot aligns with a vast underdense region, about 3 billion light-years away, the Eridanus supervoid. As light from the cosmic microwave background passes through it, it loses energy through the integrated Sachs-Wolf effect, emerging slightly colder when it reaches us. Models suggest this void explains about half of the anomaly's temperature deficit. The remainder could be due to a natural cold patch in the primordial radiation, or perhaps the void is even larger than we think. The Eridanus supervoid poses the same fundamental questions as the KBC Void. How could such an immense underdensity form at all? Is it simply a statistical outlier or evidence that our understanding of cosmic structure is incomplete? Remarkably, the void's existence was predicted by the cold spot itself, then confirmed by galaxy surveys, a rare case where cosmic temperature maps anticipated visible structure. Yet measuring its true scale remains difficult. At that distance, galaxy catalogues are incomplete and faint galaxies are easily missed. Estimates suggest a density 20–30% below the cosmic average, much like the KBC Void. If both are real, the odds of such enormous voids appearing within standard LCDM cosmology become uncomfortably slim. A few such anomalies might fit within statistical noise, but several would force a reconsideration of how structure truly forms on the largest scales. These immense voids do more than challenge theory, they distort our measurements of reality itself. They subtly alter the apparent temperature of the cosmic microwave background, and the motion of galaxies through gravitational bulk flows. Such effects are small but measurable, and they reveal that voids are not merely gaps in the cosmos, but active agents shaping what we observe. This realization connects directly to one of cosmology's most enduring mysteries, the Hubble tension. When astronomers measure the universe's expansion rate nearby within about 2 billion light-years, they consistently get a higher value, around 73 km per megaparsec. But when they measure using the ancient light of the cosmic microwave background, the value drops to 67. The boundary between these two regimes lies suspiciously close to the estimated edge of the KBC Void. That coincidence led to the Hubble bubble hypothesis that we live inside a vast underdense region, expanding slightly faster than the cosmic average. Measurements taken within it are biased, like trying to gauge Earth's climate from inside a greenhouse. This hypothesis makes a clear prediction: the measured Hubble constant should decline with distance. And indeed, recent studies show that as astronomers observe farther supernovae, the inferred rate of expansion gradually falls toward the global value. The trend isn't yet conclusive. Distant supernovae are faint and difficult to measure precisely, but the data increasingly fit the bubble model. If confirmed, it would elegantly explain the Hubble tension without invoking exotic new physics. The standard cosmological model would remain intact. We would simply occupy a statistically unusual low-density pocket of the universe. Yet the implications are unsettling. It means many of our most precise measurements are locally biased. We are quite literally inside a cosmic bubble that distorts our perception of universal truth. The only remedy is to measure beyond it, to peer farther than 2 billion light-years with enough precision to escape our local gravitational influence. Instruments like the James Webb Space Telescope and next-generation ground observatories are beginning to do just that. Early findings hint that the distant universe expands at the slower, globally consistent rate predicted by the cosmic microwave background. More data will tell whether the bubble truly resolves the tension, or if something deeper, perhaps new physics, still lurks beneath. the concept extends beyond expansion. Measurements of galaxy motion reveal strong bulk flows up to a few 100 million light-years, then fading beyond just as expected if we inhabit a void. Baryon acoustic oscillation discrepancies also cluster at low redshift, again local effects. Multiple lines of evidence converge on a single conclusion: our region of the cosmos is different. We live in an island of rarefied space surrounded by a more typical universe. But voids don't just skew what we see, they alter what can exist. In dense regions, galaxies collide and merge, frequently driving rapid evolution. Clusters filled with hot X-ray bright gas forge massive elliptical galaxies while quenching star formation. The result is red and dead galaxies, old and quiet, stripped of their raw material for new stars. This is how the crowded cosmic web evolves, fast, violent and transformative. Voids, by contrast, are still young. Their low density weakens gravity, preventing large structures from coalescing. Small galaxies can form, but massive clusters cannot. Evolution stalls. These galaxies live in cosmic solitude, isolated, gas-rich and slow to age. They continue forming stars quietly for billions of years while their denser counterparts burn out. In this way, voids act as a cosmic filter, halting the natural progression of structure. They are the quiet backwaters of creation, places where the universe still whispers its early secrets. Understanding voids, the cold spot, the Eridanus, supervoid, the KBC Void, and the bubble we may inhabit means confronting an uncomfortable truth: we may not be seeing the cosmos objectively. Our instruments, no matter how precise, measure from within a unique and possibly misleading vantage point. The patterns we call universal might instead be local echoes of a deeper, more complex reality. Yet within that limitation lies wonder. To know that we live inside a cosmic bubble, to realise that the very emptiness around us shapes our perception of the universe, is to glimpse the profound connection between observation and existence. The universe is not uniform. It is patchy, textured, alive with voids and filaments. And somewhere in that web of darkness and light, we are measuring, questioning, and learning, tiny observers, trying to understand a vast, imperfect cosmos that refuses to be simple. The cosmic filter shapes not only galaxies, but the vast intergalactic medium, the diffuse gas between them. In crowded regions, this gas is scorched to millions of degrees by galactic collisions and the furious output of supermassive black holes glowing in X-rays. But in cosmic voids, far from this violence, the gas remains cooler and closer to its ancient primordial state. These quiet zones preserve traces of the early universe, neutral hydrogen, and faint filaments that form ghostly strands of the cosmic web. Because massive structures cannot easily form there, voids evolve slowly. They are cosmic sanctuaries, calm, thin, and nearly timeless, while dense regions grow richer, more chaotic, and more energetic. Over time, this contrast deepens. Filaments condense, voids empty, and dark energy accelerates their expansion. The universe's large-scale structure is becoming more extreme with every passing epoch. This great filter also raises profound questions about life. If advanced civilizations require stability, voids might offer safety from cosmic catastrophes. No nearby supernova, no gamma-ray bursts, no black hole outbursts to sterilize worlds. Yet their calm comes at a cost. Star formation is rare, heavy elements are scarce, and the galaxies within are poor in the materials needed for complex chemistry. Voids might cradle life in peace, or starve it in silence. Whether these empty regions enhance or hinder the rise of intelligence remains one of the universe's great open mysteries. The far future of voids will be defined by isolation. Dark energy is steadily stretching space itself, pushing unbound structures beyond one another's reach. Already the process is underway, but it will accelerate beyond comprehension. In time, galaxies in voids will drift apart faster than light can bridge the distance. Superclusters like Laniakea and Shapley will vanish beyond the cosmic horizon, unable to communicate or even be seen. The cosmos will fragment into lonely islands floating in an endless sea of nothingness. For galaxies deep inside these voids, the isolation will be absolute. Light from distant structures will no longer arrive. The cosmic horizon will shrink as expansion quickens and the night sky will grow increasingly bare. The cosmic microwave background, the last echo of the Big Bang, will fade into undetectable wavelengths. Future astronomers in these silent galaxies will see no sign of an expanding universe, no trace of its origin. To them, the cosmos will appear static and eternal, an illusion created by the limits of light itself. They will live in ignorance of the vast ancient story we can still read today, a haunting thought known as the dark future. Even here in our local void that fate awaits, in roughly 4 billion years, the Milky Way and Andromeda will merge to form one giant elliptical galaxy, Milkdromeda. It will be the heart of our small gravitational island, but the rest of the nearby universe, Virgo, Leo, Spur and beyond, will slip away into the unreachable dark. Star formation will fade as the last gases are spent. The skies will dim. Trillions of years later, only aging stars, white dwarfs, neutron stars and black holes will remain. Eventually, even black holes will evaporate through Hawking radiation, leaving behind a thin mist of particles expanding forever. The universe will cool toward absolute zero, an endless ocean of silence and space, a cosmos ruled by voids. This destiny depends on dark energy continuing as a cosmological constant, steady, relentless and unchanging. If it remains so, the cosmic web we see today is just a temporary phase. The true future is one of emptiness where only isolated galaxies persist in an ever-widening void. We live in a rare moment of cosmic clarity when the universe is still bright and structured enough to study itself. One day, all that structure will dissolve into invisibility, leaving only the vast eternal quiet. If we indeed inhabit a cosmic void, the KBC Void, then another question emerges: are there others like us out there, hidden in similar deserts of space? Life depends on the distribution of matter. Galaxies must have enough heavy elements to form planets, yet not so much activity that life is constantly erased by cosmic violence. Voids may provide long, tranquil ages for life to evolve, protected from frequent cataclysms. But they also lack the raw materials and nearby neighbours that make panspermia, the transfer of life between systems, possible. Each void civilization, if it exists, would likely rise alone. Such civilizations would face a very different night sky. A species evolving inside a dense galactic cluster would quickly uncover the truth of cosmic expansion. Countless galaxies at varying distances, clear evidence of motion and age. But in a deep void with only a handful of faint galaxies in view, cosmic understanding would be far harder to reach. Their scientists might conclude the universe is static, eternal, and small, never realizing that their horizon hides everything else. Even our own cosmology could be shaped by our location inside the KBC Void. We assume our measurements are universal, but what if they're local distortions of a deeper reality? If the cosmos beyond our void looks different, our entire framework may one day need to change. The search for life has focused on habitable zones around stars, the right temperature, the right chemistry, the right light. But perhaps we must think larger. The very structure of the cosmic web may define where civilizations can thrive. Voids might produce slow, stable civilizations with patience measured in eons, while dense clusters breed short-lived bursts of brilliance extinguished by chaos. If we are typical of void dwellers, then out there across the silent reaches, other minds may be pondering the same cosmic riddle, staring into equally empty skies, asking whether their view of reality is incomplete. We are drifting within a cosmic cavity nearly 2 billion light-years across, not a metaphor, but an observed fact. The KBC Void is real. Its presence bends, light alters our measurements, and challenges our models of the universe itself. Whether it explains the Hubble tension, or merely exposes how limited our perspective is, one truth stands: the universe is far stranger than we ever imagined. Our home is not in the crowded heart of creation, but in its quiet outskirts, among the most silent spaces known. We are cosmic castaways marooned in an expanding sea of darkness, studying a cosmos that may already be slipping beyond our reach. Yet that very isolation may be what allows us to see clearly briefly the astonishing truth of existence. The universe began in fire, it will end in silence, and in between, for a fleeting moment, consciousness arose to ask why.